Right. So in this lecture, we are introducing a method of solving non-homogeneous linear systems using matrix exponentials and Laplace transforms. So we illustrate using this question: solve the following non-homogeneous system using matrix exponentials and Laplace transforms. Okay. So we just need to remind you that we can do matrix exponentials using the usual the series expansion for the matrix for the exponential function e to the power at like this. And you can now tell that if you substitute t is equal to 0, then e to the power a times 0 is actually what an identity matrix. And I just decided to call it x naught for some reason that will be clear later. So what then we do is to break this non-homogeneous system into the associated homogeneous system. Okay, so then we are pulling out the homogeneous system, 3 minus 1, 1, x. Usually, this is where you define the initial conditions. Okay, but we don't have them here. So we just have to put the vector c, which could be c1, c2 in general. But when you have the initial condition, you will basically be able to find c1, c2, or in general, the vector c. Now, so we need, we also saw that e to the power a t is actually a fundamental matrix. And we know that if e to the power at is a fundamental matrix, then the solution e to the power at is a solution of the homogeneous system. And of course, in general, we then have x of t is e to the power at times c. That's the general solution of the homogeneous system. So we want now to then solve this homogeneous system. We now rewrite it as x prime is equals to ax, where our a is 3, 1 minus 1, 1. All right, so now what we do is to apply the Laplace transform on this system. Laplace transform. So what we're going to do is to then let the small x of s be equal to the Laplace transform of the vector x. Okay, the capital letter x. So now we're applying the Laplace transform. This is actually equal to the Laplace transform of ax. So here we'll get s times the small x minus x naught. Take note, this x naught is not equal to x of 0, which is the initial condition. This x naught is equal to e to the power a times 0, which is just I. So I needed to differentiate that, lest you get confused with the two. And then this is just A times the Laplace transform of X. So then I can bring the X of S, the left-hand side. So I now have Si minus A times X of S is then equal to X naught, but we know this S naught is actually equal to I. Then it leaves us with X of S is equals to the inverse of S minus A, Si minus A. And then your e to the power at will then be the inverse Laplace transform of the inverse of S I minus A. So once we get this, then we know that we can write our solution as e to the power at. Okay. So what it means is we need to generate Si minus A. This is S00S minus our A is actually 3, 1, 1 minus 1, 1, 3, 1 minus 1, 1. And this will give us S minus 3. Then we have minus 1, 1, S minus 1. This is our Si minus A. So we want now to calculate Si minus A inverse. This will then be, the determinant here would be 1 over S minus 3 into S minus 1 plus 1 into here S minus 1 and S minus 3 exchange positions. Then these ones change signs. And if you simplify that denominator, you will then find that it gives you S minus 1 over S minus 2 squared. And then it gives us the following expressions. S minus 3 over S minus 2. So here now we need to apply our partial fraction decomposition techniques, because remember we want to find the inverse Laplace transform. So here you can see that the first one will give you 1 over S minus 2. I think it's plus 1 over S minus 2 squared. And this one is, it just remains as 1 over S minus 2 squared. All right, then this one remains as minus 1 over S minus 2 squared. And then this one would be 1 over S minus 2 minus 1 over S minus 2 squared. All right, so then we are just almost complete. So e to the power now the inverse Laplace transform of Si minus A inverse, which is the inverse Laplace transform of. Now you then need to go through your Laplace transforms. S minus 2 plus 1 over S squared, where S is replaced by S minus 2. And then 1 over S minus 2, 1 over S squared, when S is replaced by S minus 2. Okay. Then here, minus 1 over S squared, S is replaced by S minus 2. Then here we have S1 over S minus 2 minus 1 over S squared, S replaced by S minus 2. Okay, these are transformations uh, these are Laplace Laplace transforms where you have a function f of t is multiplied by e to the power at. So we just want to do the reverse of that. Then this will give you now the inverse of Laplace, the inverse Laplace transform of s over 2 is e to the power 2t. And then the inverse of Laplace transform of 1 over s squared is t. But because we have this, is then e to the power 2t. And then we now have also t e to the power 2t minus t e to the power 2t. And then here we have e to the power 2t, and then times what? Sorry, t, not t. Okay, yes. E to the power 2t minus t e to the power 2t. So one can easily see that e to the power at is equal to e to the power 2t into 1 plus t minus t, 1 minus t. So this is our fundamental matrix. And hence we can then say the solution to the homogeneous system is then equal to e to the power at times c. That this is then equal to e to the power 2t into 1 plus t minus t, 1 minus t. And we are done. You may want to check the obvious, just to check if this is correct. Let's just check. We know that this one is times c, times c, the vector. So we know that e to the power at, a times 0 should be equal to I. So let's see, this will be 1, 1, 0, 0, 1. So it is I. So this confirms that our computation is quite correct. So there we are. We have our homogeneous solution. So now we move to the the integral solution. Integral solution. It has xp is equal to e to the power at, the integral from t naught to t, e to the power minus as f of s ds. Now, we may assume without loss of generality that x of 0 is equal to c, something like that. So, okay, the initial condition is actually x of 0. Initial condition is defined. T equals 0. So then t naught becomes 0 in this case. Okay, so this is xp. So what we do, we want to calculate this. So e to the power minus as at is then equal to e to the power a, where we replace t with minus t, then this will be equal to e to the power minus 2t, and then inside we have 1 minus t, 1 plus t, after replacing t by minus t. And we want to multiply minus a is, okay, what is f of s? F of t here is given in the original question. Minus 2, 1 times e to the power 2t. So that's minus 2, 1 times e to the power 2t. So now e to the power minus as f of s is just replacing t with s in e to the power at and ft. So this will be e to the power minus 2s. Then I take this 2t here, e to the power minus e to the power 2s into 1 minus t minus t1 plus t times minus 2, 1. And we can see these two cancel off. So this is just now 1 minus t times minus 2. So that's minus 2 plus 2t, and then minus t. And then here it's minus 2t plus 1 plus t, which is just minus 2 plus t, and then minus t plus 1. This is the product. So now xp, now compute xp. So xp is equal to e to the power at times the integral from 0 to t e to the power minus as times f of s respect to s. So this is e to the power at times the integral from 0 to t of minus 2 plus s. Okay, why were we using t here when we were supposed to use s? This was supposed to be s because we were dealing with s there. So everywhere where there's t, we put s, put s, put s, put s. Okay. So that's minus 2 plus s minus s plus 1 s. And this will just give us e to the power at times, now here we're going to have minus 2s plus s squared over 2 minus s squared over 2 plus s evaluated from 0 to t. Okay, and this is e to the power at times this vector minus 2s minus 2t plus t squared over 2, then t minus t squared over 2. And all we need to do now is to then unpack, we bring it the e to the power at here, which is then equal to e to the power 2t into 1 plus t, what was that, 1 minus t, let's see, no, t minus t, 1 minus t, times t squared over 2 minus 2t minus t squared over 2 plus t. Okay, so this is now e to the power 2t into, now we have t squared over 2 minus 2t times t plus 1 plus t into minus t squared over 2 plus t. All right, then here we have minus t into t squared over 2 minus 2t, and then plus minus t squared over 2 plus t into minus t plus 1. And then the rest is left as an exercise. This is just an algebra exercise. Finish off. And then you will then now write the general solution will be e to the power 2t into 1 plus t minus t, 1 minus t times the vector c, and then plus e to the power 2t into the whole of this here. And you have your solution. And take note that because we do not have initial conditions, then C remains just a general vector of constants of integration.